welcome Professor Mamdud Hussain from RGU UK. He is our international speaker for our FTP program. So I'd like to introduce our chief guest today with some remarks. Mamdud Hussain is a professor of future studies at School of Engineering and leads the Energy Research Group made up of 10 academic and 35 PhD students. His research interest includes applying computational modeling techniques to solve some of the most challenging and interesting problems related to hydrogen fuel cell, tidal, wave, and wind energy, and multi-phase flow for oil and gas industries. So, sir is done. So, I almost attended many conference and many research work, and is a member in many review committees for and Commonwealth Scholarship Program and Commission. So, and also, sir is a senior fellow of Higher Education Academy and Chartered Engineering and member of IMEC Engineering. So it's my honor to have with us such a wonderful, yeah, renowned speakers in this field of green hydrogens. So I welcome you, sir. Now I hand over the session to Professor Mamdud Uzain, sir. So over to Professor.
Thank you very much for your kind introduction. So I will start my presentation in a second. Let me sort this technology out. Screen now.
Yeah, its screen is visible, sir. Yes.
And is it
It's yeah, it's a full
move,
moon. Sir. Yes.
is it moving?
Yes, moving, sir. It's moving.
Okay.
It's
So
fine.
can you hear me all clear?
Yes, sir. Yes, professor. It's audible to
Okay.
us.
So let me start today. Thank you, first of all, for your kind invitation to give a talk here and also your kind introduction. As I said, my name is Mamdud Hussain, and I am a fellow of IMECI and also senior fellow of Higher Education Academy. Today, I'm going to talk about role of hydrogen in achieving net zero. I will give you a lot of background in this area, and then we'll talk about the type of research we are doing at Robert Gordon University. I'm a professor here, and my work is on future energy technology. Basically, my role is to look at what type of energy we are looking at in 2030 and beyond, and do the research proactively from now on. And I worked primarily on hydrogen, but I also work on broader energy domain. Okay, a little bit of my biography. I originally came from Bangladesh. I did my undergraduate study in 1994 in Bangladesh, and then I did my MSc again in 96 in Bangladesh. I came to UK to do my PhD and completed in 1999. In 2000 to 2006, I worked as a research associate at a number of universities, including Loughborough University and University of Nottingham. In 2006, I joined Robert Gordon University as a lecturer, and I stayed lecturer until 2012. In 2012, I was promoted to reader, and in 2021, I was promoted to full professor at Robert Gordon University. This is one of the news of our recent research work. Uh, we have been working on hydrogen production, and we have made significant breakthrough in high temperature steam-based hydrogen production. And this work has been reported in a number of uh, news portal and TV interview, and a newspaper interview, and so on. Okay, we have a team, and I will introduce my team further down the line. A little bit about my university, because it's always customary to promote my university here. So if you are familiar with map of UK, uh, we have uh, Scotland is England here, Wales here, Northern Ireland, and Scotland. And most of this activity actually happen what we call central belt around this area. And our university is further up north, northeast of Scotland. At this point here, Aberdeen. The place is called Aberdeen. It is on North Sea, and where I am putting my cursor here, this area is full of oil and gas installation. So offshore oil and gas. Uh, Aberdeen is the capital of oil and gas in Europe and throughout the world. And this area is full of oil and gas platform and its installation. Where I put my cursor here, this area is now transformed into offshore wind energy. So gradually, Aberdeen and UK is moving away from oil and gas and into renewable energy. Also, this Aberdeen is a hub of hydrogen. So I will talk about hydrogen activity later around Aberdeen area. This is our campus here. It's a very new campus, and it's one of the small university in UK. We have only 18,000 students compared to many of the university where they have 100,000 students. Um, our university is number one in Scotland and number two in all over UK in graduate employment, because most of our graduate, or more than 99% of our graduate, is in employment within 6 months of graduation. This is our campus I just showed here. Is on the bank of the river. It's a very green and very modern building we have. And this is tower. This is our library. If you go to the top of the tower, you can have a beautiful view of Aberdeen. And I will welcome you if you have opportunity to come to Aberdeen. I will welcome you to come and visit us. Uh, 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 Now I'm going to talk about some of the background of energy supply, population, and GDP, and how these three things interlinked with each other. So first of all, if you look at carbon dioxide emission, uh, uh, why we are talking about carbon dioxide emission? Because world need more energy as the population grow, as the economic grow of many of these countries, we need to have more and more energy. However, the largest source of energy we have, which is oil and gas, that also largest source of CO2 emission. If you look at this curve here, over the year from 1850 to 2021, if you can look around 2000, from there on 45% of all carbon dioxide emissions actually happened in the time between 1990 and 2021. So carbon dioxide emission accelerated due to use of energy and industry emission. And the impact of carbon dioxide emission we can already feeling. We are global warming is happening now due to carbon dioxide emission, and we can see prolonged drought, cyclone, flood, sea level rise. Because I came from Bangladesh, though I have been here for a long time, but I heard that sea level is going up in Bangladesh and a lot of the low lying areas is going underwater. Then we have extreme heat events and increased flood and water insecurity, damage to freshwater, coastal and ocean marine ecosystems. So a lot of impact happening due to carbon dioxide emission. So what we need to do, what we can do to prevent that? Before you can do that, we can see that there is a link between global energy use and GDP. So if you look at this curve, obviously the global GDP is going up. Many of the people are getting benefit from what we call is a free free economy and free trade and things like that. So global GDP is growing up. At the same time, we can look at the energy consumption also following the GDP. So you have to remember that as the GDP growth going up for every country, is energy consumption also going up. So there is has been tremendous increase in the growth of energy supply in the last 150 years. However, the population growth is also going on, and many of the people uh, uh, cannot afford renewable energy. Also, as you said here, if you look at per capital energy consumption, is actually related to economic growth again. So if you look at this curve again, you can see right hand side we have USA, we have Germany, we have UK, Japan. Then population is actually low, while in China we can see the big bubble, which population is high. India here, big bubble, uh, population is high. Bangladesh is here. We are still at a low economic developing countries. Uh, However, as you said, the higher the per capita GDP, it looks like higher the uh, energy consumption per unit head kind of thing. However, now what we are looking at is economic growth is happening because many of these low income and developing countries, they are growing rapidly, so their energy demand will go up. So what you need to do, if you have this type of energy demand going up and up, we have the risk of uh, getting global warming. Obviously, we have already feeling, but its impact will go up. So what we need to do, we need to transition to sustainable energy rapidly to avoid the worst risk of climate change. What you require is to reduce, first of all, carbon dioxide emission first, and ultimately eliminate carbon dioxide emission or greenhouse gas emission completely, because our aim is to keep temperature rise to 2 degree at pre-industrial time. Okay, so we have to keep it at 2 degree. uh, we don't want to global temperature to go up more than 2 degree from the pre-industrial time. So what we need is massive, immediate and sustained effort. So these are the words. We need immediate, massive and sustained effort in reducing carbon dioxide emission. What it means is that we actually need to move rapidly into substance, uh, to transition to sub sustainable energy system. So we need to transition to sustainable energy system. That's the goal. So what are the sustainable energy system? We have lot of different type of sustainable energy. We are going to look at it. Already is happening actually. There is a strong sign currently that we are investing in clean energy or sustainable energy. So if you look at oil and gas line, actually is coming down here. Natural gas use is coming down here, whereas low emission power is going up. Even in USA, they are spending on if they are spending $1 in oil and gas, they are spending $1.8 in clean energy technology. So we have seen a increase of spending in low emission technology. But this increase in spending is actually happening in advanced economies and in China. Okay, so another interesting graph here. If you look at GDP, which is a light green color, and fossil fuel demand, which is white color here, or sorry, black and white color here. If you follow the green here up to this point, the economic GDP growth and use of fossil fuel was going up hands in hand. But from 2022, the link between GDP is still going up. However, the fossil fuel demand is set to come down. So this historic link between GDP and fossil fuel demand is set to get decoupled. And so if you think about 2050 or 2040, we can see that about 70% of the electricity is generated from renewables. If you go back 1975, 70% of electricity is produced from fossil fuel. So from 1975 to 2050, it will flip, where 70% of electricity will be generated from renewable energy. Solar PV has already become a larger source of electricity generation. If you go back again here, interestingly, um, uh, advanced economies consume two-thirds of fossil fuel globally in 1975, and we expect that to flip again, and then emerging market and developing economies will consume two-thirds of fossil fuel globally by 2030. So it's changing happening. And by 2002, we have 600 million cars on the road globally. And by 2040, we'll have 650 million electric cars on the road globally. From moving on from petrol and diesel car, we are actually moving on to electrical car rapidly, and it started to happen now. So, but there is still a lot of challenges that we need to meet uh, in terms of looking at clean technology, which is surging ahead, and the main technology which is well ahead of the plan for 2030 scenario is solar PV. So if you look at 100 achievement of 100% planned activity to achieve net zero emission scenario by 2030, PV projects are already there. Other technology is lacking behind, especially hydrogen here. Heat pumps quite behind. Heat pump is needed for heating the room in the cold countries. Wind energy, though we see a lot of wind energy everywhere, but it still is quite behind solar technology. So a lot of things happening and accelerating. So that is positive news. However, there are some of the what do you call a very difficult uh, scenario where solar PV or wind cannot work and cannot be used for decarbonizing. There, the role of hydrogen become more important. The role of hydrogen in energy transition become more important in some of the sector. So hydrogen is a versatile energy carrier. So that's the important thing. It's versatile and is a key to decarbonize a number of difficult sectors. So again, there are a number of sectors which is not easy to decarbonize. If you think about electricity generation, it's easy to decarbonize. You can use solar energy, you can use wind energy, wave energy, uh, micro turbine, uh, and uh, and then decarbonize electricity generation. But some of the transport, if you think about some of the long distance transport, especially aeroplane, especially shipping, is very difficult to decarbonize using battery technology. So in those cases, hydrogen may play a significant role. Okay, so there are a lot of advantage of hydrogen because it can be used in many different ways. So it can be used for electricity generation, and that electricity generation could be distributed, remote, standalone, backup using fuel cell. Then transport, it can be used in car, bus, truck, forklift, train, using using fuel cell. Then you can use in chargers, something like charging your mobile phone or laptop using fuel cell. Domestic heating and electricity, you can use in a fuel cell. Domestic heating and cooking, you can blend with existing gas to provide heating and provide cooking at the intermediate stage, and then we can move on to completely hydrogen through combustion. We start off with blending and then moving on to 100% hydrogen. Similarly, you can decarbonize truck and digger blended with diesel and use existing engine. It can be used for energy storage as a source of energy storage and load balancing for intermittent renewable energy. So you produce uh, hydrogen, you store hydrogen, and then you reuse it when needed. So it's a source of energy storage and a medium of load balancing. So if you have so much advantage of hydrogen, why you are not using hydrogen? Okay, so this is the challenge. What is hydrogen? If you look at periodic table, hydrogen is a gas. It is a colorless, odorless, tasteless, non-toxic. So if you look at these properties, that also give you some clue. Because if there is a hydrogen leakage, you cannot see it, you cannot smell it, you cannot taste it. And the problem is it's highly combustible. So it combusts in air with small proportion with large proportion. The flammability limit is very, very high. Flammability limit is very, very high. So if it is highly flammable and if you cannot see it, feel, taste it, or smell it, so that's the danger. Um, its density is very low. If you think about air density, 1.18 kg per meter cube, hydrogen density is comparatively very low. So that also gives you some clue about how we are going to store hydrogen. Because density low, you need a large volume, so you have to compress it, put it under high pressure, and so high pressure storage becomes a challenge again. Hydrogen is available everywhere. If you think about hydrogen, is the most abundant chemical element, contribute to 75% of the mass of the universe. So hydrogen is everywhere. However, here is the problem. Hydrogen is very scarce as a gas. We don't see hydrogen available in a gas because hydrogen is actually atom is combined with water in natural gas in plant. Hydrogen atom is not hydrogen molecule is not available on its own. It's combined with something else, and we have to break those something else to produce hydrogen. So hydrogen can be produced from natural gas, from water, and from biomass. So they are the three sources. There are other sources also, but primarily we have to produce hydrogen. Hydrogen as a gas is not available in nature. Hydrogen as a gas is not available in nature. Then so when we are producing hydrogen, we actually color code it to for the benefit of our scientists, researchers, and policymakers. What type of hydrogen we are producing? First of all, we can call it a gray hydrogen. Is produced from fossil fuel, natural gas, and coal. What's the disadvantage of coal, gray hydrogen? During the process, we produce carbon dioxide and we emit carbon dioxide into atmosphere. So gray hydrogen is not a, a process which is led to carbon dioxide emission. Then we have blue hydrogen, which is again produced from fossil fuel, but it's supported with carbon capture and storage. So whatever carbon dioxide used during production of hydrogen from fossil fuel is stored. So we call it a blue hydrogen. Then we have a turquoise hydrogen, which is uh, produced from fossil fuel using a process called pyrolysis. Advantage of fossil fuel is that you get the carbon as a solid product during pyrolysis process rather than gas coming out. So you can store it a little bit better. Our objective is to produce green hydrogen. So green hydrogen is produced from water using electrolyzer. We also need electricity, and that electricity is generated from renewable source. So green hydrogen in the process it doesn't emit carbon dioxide because it needs water, it needs electricity, and electricity coming from renewable source. Then we have purple hydrogen, which is produced again from water splitting using electrolyzer. However, the electricity and the steam coming from nuclear plant. So that's also kind of a zero emission hydrogen production. And now we have a yellow hydrogen, which is again produced from water splitting using electrolyzer. But in this case, we are using grid electricity. So first three process is actually coming from uh, coming from natural gas, and the last three processes coming from water splitting. So water has this input. Okay, so we can use hydrogen. As you said, we need electricity or some source of energy, and that can come from renewable or non-renewable sources. Still, today, 95% of water is still, sorry, 95% of hydrogen is produced from methane using a thermocatalytic process. But this process, as I said, create global warming because this process releases carbon dioxide. So if you think about three different process, one is steam reforming, one is electrolysis, one is biomass gasification. It has been researched and shown that biomass gasification has been the best energy efficient in terms of producing hydrogen for the time being. But in future, electrolysis will be the number one. Okay, and steam reforming, 95% of hydrogen is produced from steam reforming now, but that actually release carbon dioxide into atmosphere. So that's not a good process. Anyway, let's look at how we can produce hydrogen as an industrial uh, space. This is actually a very mature technology. It has got methane. We mixed it steam at 700 to 1000 degrees Celsius under the pressure of 3 to 25 bar process, and in presence of a catalyst. We need a catalyst called nickel to produce hydrogen and carbon monoxide in the first step. So you get your methane, you get your steam, apply heat and pressure. In presence of catalyst, it produces carbon monoxide and uh, hydrogen. And this carbon monoxide again react with steam in the next stage and further produce carbon dioxide and H2. So this is a two-step process. Methane produces carbon monoxide and uh, hydrogen, and this carbon monoxide subsequently react with more steam to produce carbon dioxide and hydrogen. Then, of course, we have to clean up and then produce clean hydrogen. This is the process here. In this steam reforming process, the main chemical kinetics uh, is limited by catalyst. The type of catalyst give you the faster chemical reaction. So if you look at this chemical reaction happening in this here, we need to have a catalyst, and this type of catalyst is actually nickel catalyst is used 10% to 15%. This is dispersed over a alumina based support. So you have a refractory medium which is alumina based support structure. You embed nickel on top of this structure, and that act as a catalyst. So these are some of the figure of catalyst here. These are alumina or aluminum oxide tube kind of thing, a pellet kind of thing with number of holes, and you put nickel on top of that, and that catalyst actually enhance your chemical reaction because it allow hydrocarbon molecule to be absorbed and dissociate at metal side here, nickel side, and also allow water to be absorbed on metal oxide side. Once it absorbed, then it do a surface chemical reaction, migrate and surface chemical reaction to produce break up hydrocarbon. So steam and hydrocarbon is actually uh, adsorbed on the surface of this catalyst, and then chemical reaction take place, and that's the role of catalyst. So catalyst is the heart of hydrogen production, steam reforming, and if you can develop a better catalyst, of course, you can improve the production rate, purity, and selectivity. So nickel particle size is physiochemical properties on the support and support metal interaction that give you the better catalytic reaction. We can produce hydrogen from biomass. Biomass is, we call it a renewable source of organic source, and biomass include a lot of agriculture crop, forest residues, uh, organic municipal solid waste, animal waste, and things like that. We can use two different techniques on its pyrolysis, on its gasification to produce hydrogen from biogas. So if you look at a little bit in details, we have more biomass available in the world than is required for food and animal feed. So we have a large source of biomass available. And the way to think about it is biomass recycles carbon dioxide. How? if you plant a plant that consume carbon dioxide from atmosphere, offsetting the carbon dioxide produced during the gasification of biomass into hydrogen. So when you are gasifying biomass into hydrogen, you release carbon dioxide, but that carbon dioxide is then consumed by plant. Then you take the plant out and use biomass again to produce hydrogen. So this is a recycle of carbon dioxide. You are releasing carbon dioxide on the one hand, on the other hand, you are consuming carbon dioxide in the plant in the biomass. So what is the technique for biomass gasification? And what type of material we can use? We can use a lot of material, something like woody materials, stem, branch, leaves, bark, chips of various trees. We can use agricultural waste, something like straw, shells, flour, grass. We can use aquatic minerals, microalgae, microbes, blue algae, fungus. We can use human and animal waste, manure of human animals, wasted food, paper, plastic pulp, and industrial waste from sugar mills, paper mill, food processing industry. So biomass is abundant, widely available in nature, and it can be a source of 10% of world's primary energy by 2030. What is the challenge of biomass? This is the challenge. If you look at different type of biomass, source is water or moisture content is quite different. If you look at cattle manure, water content is 88%, rice straw 50 to 80%, some of fir tree 6.5, Danish pine 8%, rice husk 7 to 10%. So water content it varies significantly in order to treat biomass. And if you heat, most of the heat will go into vaporizing moisture. Okay. So in terms of chemistry of gasification, we can use air, we can use pure carbon oxygen, you can use steam, mixture of steam and air, oxygen and steam as a gasification agent. And when you have a gasification process, at the end, what you get is hydrogen, carbon monoxide, carbon dioxide, and methanation. And we can use, if you use oxygen steam or steam as a gasification agent, we can get a byproduct of hydrogen and carbon monoxide as a syngas type product, temperature at 800 to 1600 degrees Celsius. If you use air as a gasification agent, we can use slightly low temperature, that's fine, but you have main component is nitrogen. So massive amount of nitrogen, you need to heat it up, but it doesn't do much into your process. Okay, so what are the product of biomass pyrolysis? How it works? So you have biomass. If you pyrolyzed it, that means you heat it in presence or in absence of oxygen, is a thermochemical process. Uh, the type of product we get is primary gas, heavier vapor, and primary char is like a solid product. Then this heavier vapor turn into tar and primary gas into gas, and some of the char and heavier gas in the next step also produce gases. So we are interested in the gas. We ended up with some source of tar, which is very viscous, liquidy, black type material, and also you ended up with char, which is kind of solid waste. So these two are unwelcome product of this gasification process or pyrolysis process. Okay, so let's look at some of the chemical reaction. We have at the end we have biomass which create uh, large heavy molecules of vapor to begin with and light gases including hydrogen, carbon monoxide, methane, carbon dioxide, some of the steam coming out, and primary char. So those large molecule that can turn into tar, and these are solid particle, and these are the gas. So then you have to decompose those tar in terms of chemical reaction. From heavy vapor you can again get light vapor, you can get lot of lighter gas, and tar can subsequently react with steam and things like that, produce further hydrogen. And some of the stars then go through polymerization and create a longer chain, uh, uh, kind of a black type oil structure. Okay, so basically you get a lighter gaseous product, some liquid product, and some solid product, and lot of chemical reaction go through methanation. Is methane reforming is one. When you have a methane, you can again react with the steam and get hydrogen out. You have water gas shift reaction. It can happen in presence of carbon monoxide and water, producing further hydrogen and carbon dioxide. Uh, you can steam act directly with the carbon, some of the tar, some of the char, and produce hydrogen and things like that. Water gas shift reaction, Bodard reaction, which is carbon plus carbon dioxide, creating carbon monoxide. Some of the carbon and hydrogen react to produce methane also. So, lot of chemical reaction going on, and that led to hydrogen, sometimes hydrogen production, methane production, carbon monoxide, and carbon dioxide production at the same time. Uh, what are the parameters that affect biomass pyrolysis and hydrogen production? It include uh,
అదేంటి గానే ఉన్నది అవు
if you have
మనిషిగాడు
is that problem,
No,
hello,
sir. Please, sir. Sorry.
is it all
Somebody
okay?
is disturbed. Yeah, it's okay, sir. Okay, bro, sir.
Okay, so what are the biomass pyrolysis and uh, what are the parameters that impact biomass pyrolysis? So the main impact is the we need to have biomass with higher cellulose and cellulose material. So then we can get a higher gaseous product. Moisture content should not be more than 30%. Low ash biomass is favorable because we have, as I said, char formation and things like that. High temperature, of course, better pyrolysis. High pressure also better, but then you need to have a complex system design. And high temperature, there is more risk of producing methane rather than hydrogen. Methanation reaction can happen at high temperature and high pressure. So there are some of the challenges: cost and availability of feedstock. So you have to collect your feedstock, you have to transport it, storage it. These are all labor intensive process. If you want to maximize carbon hydrogen production, usually biomass has low elemental hydrogen. So during the pyrolysis process, it actually creates a whole lot of gases: carbon, carbon monoxide, carbon dioxide, steam, methane, ethane, and other gases. So you need to have a separation process and purification process to maximize hydrogen production. And also, it produces a lot of, as I said, liquid product, biooil, biotar. That's fine, but biotar can plug filters and tubes and process. Okay, so that's one challenge of hydrogen production through pyrolysis. Another process is gasification, which is similar to pyrolysis, and then you take the pyrolysis product and you put it through gasification agent, which is air, what, steam, or oxygen, and so you basically produce more gaseous product and less biofuel and biotar. So pyrolysis is a low temperature in absence of oxygen process, and gasification is a high temperature process. You take the pyrolysis and you uh, apply higher temperature in presence of gasification agents and produce more gas. Chemical reaction is very much similar. You have the tar and you can react tar with steam and produce more hydrogen, carbon monoxide, and carbon dioxide. And if you have methane, you can then reform the methane in presence of steam and produce more hydrogen and things like that. So that's the advantage of gasification. Is a higher temperature process in presence of gasification agent. Okay. Uh, And most of the reaction is very similar. This is a methanation reaction, carbon reacting with hydrogen to produce methane. We want to reduce that chemical reaction, so we come up with more hydrogen. Okay. Uh, in terms of gasification, we can use oxygen. We can use pure oxygen. It's an endothermic process. And partial oxygen provides some energy, but it's very costly process. We can use air gasification, which is cheaper, but which is diluted with vast amount of nitrogen. Then we have a steam reforming process, as you talked about before, which reform the tar, because tar is a kind of a liquidy, black, oily residue. We can use steam to reform that and produce further hydrogen to release it from there. So oxygen has got advantage. Air has got cheaper. Easy to use. Steam reforming is, of course, you have to get water, which is kind of free, if you can call it, but you have to turn into steam. So you need a boiler and water treatment process. Pure oxygen, getting it difficult and also is very costly. So before I move on to the next topic of green hydrogen, probably I will give you a 2 or 3 minute break, or maybe 3 minute break, to absorb what I have discussed till now, and we'll start exactly at what will be quarter to after 3 minutes, basically, and we'll move on to green hydrogen.
Okay, Professor.
Is that okay?
That's so fine. That's fine.
Okay. So just in 3 minutes, we'll reconvene here.
Okay, sir. Okay.
Okay, can you hear me again?
Yes, sir. Yes, sir.
Yes, sir.
And I see it. Okay, one thing I wanted to say is that my laptop, uh, the charging is not working properly. So if I am cut off suddenly, just give 5-10 minutes. I will come back. Okay. And now we are moving on to new topic. Not topic. Continue with how we can produce green hydrogen, which is our ultimate goal. So what is a green hydrogen? In order to produce green hydrogen, we need water, we need re- renewable electricity, and we need a device called electrolyzer. Function of an electrolyzer is to split water into hydrogen and oxygen. So three things we need: availability of water, availability of renewable energy, and electrolyzer. And there are many different type of electrolyzer. Just I have highlighted two of them here. One is polymer electrolyte membrane electrolyzer, which work at low temperature, and then we have a high temperature electrolyzer, which is called solid oxide electrolyzer, which I have seen it here. So basically, electrolysis process can have low temperature and high temperature. And there are benefit of using electrolyzer at high temperature, and I will explain that further down the line. So let's focus on green hydrogen and how we can, what type of infrastructure we need for green hydrogen. Okay, so first of all, in order to produce green hydrogen, as I said, we need three things. For the time being, if you look at the uh, process of steam reforming that we talked about from methane and biomass, that type of cost is about 1 kg. Now, the cost of production of hydrogen is $1 per kg, $1 per kg. Whereas production of green hydrogen is roughly $4 per kg. So our objective is to bring this production cost of $4 per kg to below $1 per kg. Otherwise, in terms of cost effectiveness, is still methane reforming, steam reforming, or even biogas hydrogen is much cheaper compared to uh, producing green hydrogen. Okay, so bear in mind the price from $4 per kg, bring it down to $1 per kg. Why we how can we produce green hydrogen at cheaper price? There are a lot of technical challenges. First of all, green hydrogen is produced from water electrolysis. Its efficiency is 60 to 70%. That means one third of the electricity is wasted in heat. We can recover some of the heat by some clever engineering, but still is a 100% not efficient process. As I told you in the beginning, the hydrogen has a very small density. That means storage of hydrogen is a challenge. You have to compress it and then you can store it. And 10% energy is lost in compression process, or we need 10% of the energy into compression. Then if you produce electricity from this stored hydrogen, and in fuel cell, efficiency of fuel cell is 40 to 55%. Okay, so efficiency of fuel cell is actually very low because here in this process, a lot of heat is also generated and this heat is again lost. So if you have a system where you use hydrogen, green hydrogen as a storage, you produce green hydrogen from electricity, then you have hydrogen in a hydrogen tank, then you produce electricity back from hydrogen. The whole process is only 38% efficient. So that's a big challenge. You can recover some of the cost, especially from electricity, by using renewable energy, especially when you have excess renewable energy which is not needed for your use. You can use that excess energy to produce hydrogen. Only in that case, hydrogen production become economic. Okay. Another challenge is water. We don't talk about water that much when we are talking about hydrogen production, but we have to think about that. because if you want to produce 1 kg of hydrogen, it need 9 kg of water stoichiometrically. But we run our electrolyzer twice the stoichiometric uh, ratio. So we have some water going through the system. Excess water goes through the system. So in order to produce 1 kg of hydrogen, we need 20 kg of water, roughly. So we know only 1% of the world water is fresh water, 99% is saline water or dirty water. And desalination of seawater is also very expensive process. Using reverse osmosis is 50% efficient and also cost about 0.7 to $2.5 per meter cube of water treatment. So we have to think about where we are getting water from for our green hydrogen production. The main cost of green hydrogen production actually coming from electricity, which is 50 to 70% of the production cost of hydrogen. 50 to 7%. So if you can get this electricity for free, what we mean for free is that excess renewable energy when we don't need it. For example, at night time, when after midnight, when we don't need electricity, but if the wind turbine is producing lots of excess energy, then we can use that to produce hydrogen. During daytime, when you have a solar plant and it's producing a lot of electricity which we don't need, so you can use the solar plant to produce hydrogen, excess solar energy to produce hydrogen. One of the challenge of renewables is, again, it's not intermittent. Okay, so sometimes renewable energy high, sometimes low. So if you couple hydrogen production directly, electrolyzer directly with PV cell or with wind energy, you have to have a very uh, complex optimization and control system. Other challenge is fuel cell and electrolyzer depends on novel material such as platinum or OSJ and things like that. And these are very scarce material. This is high cost and resources is concentrated in particular areas. Most of these resources is actually at a location where there is social or political instability or unrest. So that's another big challenge to have a supply chain of scarce, rare material for your production of electrolyzer and things like that. So whole supply chain, establishing the supply chain is a challenge also. So what are the materials? So I have listed 1, 2, 3, 4, 5, 6, 7 type of electrolyzer, and each of these electrolyzer use different type of very expensive and rare material, and during the process also it degrade quickly. So for example, for PEM fuel cell, we need titanium plate. For solid oxide electrolyzer, we need OSJ, we need nickel, we need LSM, we need zirconia, alumina support. And on the other hand, again, nickel, alumina, nickel oxide, so titanium oxide, zinc oxide, OSJ. So these are the type of material we need, uh, and which are again uh, uh, platinum is one of those proton exchange membrane use a lot of platinum. So these are the very rare and expensive material, and these are actually available in countries which are again politically not stable. So as I said, establishing a supply chain is a big challenge for moving on to green hydrogen production. Okay, we can produce hydrogen. What about transport and distribution? How we can take it from one place to another place? Thus, we can do that by pipeline. So if you want to use hydrogen pipeline for transport, this is the challenge. Hydrogen molecule is small. It can easily permeate through material of a pipeline. And another problem, what is called hydrogen embrittlement, is hydrogen can create embrittlement in metals, especially steel. So higher the grade of steel, it is prone to more embrittlement, and embrittlement can lead to cracks and rupture in the pipeline. So higher the quality, better quality steel you have, better probability of getting it embrittle. So pipeline designed for exclusively for hydrogen, that's why, is 68% more expensive than gas pipeline. Pipeline designed exclusively for hydrogen is 68% more expensive. Hydrogen pipeline is made with lower grade steel because, as I said, higher the steel grade, more embrittlement it experience. So lower grade steel it is used, and with thicker pipe wall. Another option is to repurposing the existing pipeline for hydrogen transport. In that case, cost will be less. We can keep the cost around 10 to 15% of the new construction. Okay. We can also transport hydrogen through a trailer in a hydrogen tank. But if you want to transport trailer, say for 100 kilometer of transport through pipeline is lot cheaper here, less than 0.25 pence or 25 pence for 100 kilometer transport per kg here. If you want to transport by trailer and truck, it goes up to 3-4 pound per kg of transport. So pipeline is the cheapest option of transporting uh, hydrogen. Another interesting thing is that transporting hydrogen will be cheaper than transporting electricity. So if you turn hydrogen into electricity, and if you want to transport electricity, which could be more expensive than transporting hydrogen in a pipeline. Okay, so new project of hydrogen is coming up all over the world. That's a good thing. Hydrogen has got the attention of a lot of businessmen, a lot of politicians, a lot of policymakers, scientists, academia. So new project coming up. However, most of the project is actually used for traditional use of hydrogen. Number one, and second is most of the project is actually using gray hydrogen route. Very few, less than 1% actually, of global hydrogen production is actually green hydrogen. Though we are forecasting lot announcement every day, we are hearing announcement for new hydrogen project, hydrogen production project, but it's actually even in Scotland, which is in this corner, you can see a lot of project coming up, packed with hydrogen project in America also, in South America also, but these are, as I said, gray hydrogen kind of production. We need massive scale up of hydrogen production to meet net zero target of 2050. And if you look at this 2030 scenario, we can have traditional gray hydrogen production, and we can have then green hydrogen production on the top. Okay. Currently, not much of green hydrogen production is happening. Most of them are uh, gray hydrogen production, or gray hydrogen with some source of carbon capture and storage. USA and UA, they are working on policy domain, and China is taking lead in deployment of lot of hydrogen production and demonstration unit. China added 220 megawatt of electrolyzer capacity in 2022, and they are planning to add 750 megawatt under construction by construction now. So by 2050, we need electrolyzer capacity of 550 gigawatt, massive amount of uh, needed. Uh, However, as I said, hydrogen uh, demand is growing by 3% in 2020, but that hydrogen is used in traditional sector. These are the traditional sector of uh, refinery and metal processing and things like that. However, we need hydrogen for transporting power, building heating. We need hydrogen for electrical generation and things like that. And these are not still not coming at this moment, but in future definitely it will come. So now we are going to talk about little bit of hydrogen policy of the UK government that allow how to build hydrogen economy. Okay, so if you look at UK government policy, they have changing the policy significantly. First of all, they had a 10-point plan for green industrial revolution, and that came in 2020 November. and at that time their target was to produce 5 gigawatt of low carbon hydrogen production by 2030. 5 gigawatt. So world need 550 gigawatt. UK is proposing only 5 gigawatt by 2030. However, they revised the plan just after 2 years in April 2020. That plan is called Energy Security Strategy, and they are now proposing to produce 10 gigawatt of hydrogen, and this 10 gigawatt, 50% coming from green hydrogen and 50% maybe gray and blue hydrogen. Okay, so what is the use of target? Hydrogen demand by 2050, further down the line, it is forecasted that 20 to 35% of UK energy consumption will come from hydrogen. So that is significant amount. And hydrogen will power industry, power sector, heat in building, and transport sector. So all four sectors, hydrogen will play a role, and these are the target of using hydrogen at different sectors. Not only that, policy is this policy is funded. So there is in August 2021, UK government released first package and £2 billion worth of fund for hydrogen production. So a lot of big companies can bid to get share of this money and build up hydrogen production facilities as a demonstration level. So on top of that, we have £100 million going to heavy industry to switch to low carbon fuel, including hydrogen. Then they have Net Zero Hydrogen Fund, another special funding for development of capex and defects, which is £240 million, and also only for electrolytic hydrogen production, another £100 million is going into electrolytic project. So there is a lot of money UK government is investing to back up their policy. So if you look at the policy in a nutshell, they have supporting policy and regulatory environment. They have skills and supply chain development, demand and use, and innovation and incentive. So these four areas UK government is investing money. And so the target in a nutshell is 10 gigawatt of hydrogen production, and 50% is coming from electrolytic hydrogen. Actually, that revised up to 6 gigawatt, 60% of hydrogen coming from green source. There are different level of funding. 960 million fund for Green Industries Growth Accelerator Fund. This is the name of one fund. Another fund has got 170 million for Net Zero Innovation Profile on hydrogen innovation, and then you have another 18 billion pound available through different type of banking sector and private sector financial capacity in that. And hope is that by 2050, 35% of the energy consumption will be provided from hydrogen. And though the target is 10 gigawatt, already we are seeing up to 27 gigawatt of potential hydrogen project in the pipeline. So we are actually going over the target. So these are some of the hydrogen allocation round one and round two that is allocated to produce hydrogen of 125 megawatt and then 875 megawatt throughout the UK. So if you look at this UK map, we have up to 31 project funded throughout UK to produce green hydrogen. So we are in Aberdeen, as you said here, 29. So if you look at number 29, we have a Aberdeen Hydrogen Hub. BP, the oil company BP, and there is another company called Hydrogen Energy Limited. They teamed up to produce hydrogen from offshore wind and solar, and they will have a dedicated hydrogen park in this area. Very near to where we are, we have another one, number one. So number one is Cromarty. There is a company called Istorega. They are developing another hydrogen production facilities here, and this hydrogen will be feeding into distilleries to decarbonize the distillery wine production, especially you may know that Scotland is famous for Scotch whiskey. So there will be whiskey production using hydrogen as a energy source around this area. So that's the primary uh, project of hydrogen utilization around this area. So these are near us. Number nine is also in Scotland, which is Scottish Power developing a weekly green hydrogen from offshore, from onshore wind again. So a lot of project going on around in UK. Okay, so what are the research challenges? Still, we are a researcher, so what are the future of research? So one of the research challenge is to look at alternative catalyst, because most of the catalyst is very expensive, especially platinum used in PEM. So if you can come up with cheap catalyst, that will be great. Solid oxide electrolyzer development, that's the key issue again, because this is solid oxide is a high temperature electrolysis process, and producing hydrogen at high temperature get a lot of benefit. I will explain that in a minute. And seawater electrolysis is another big research area, how you can use seawater either directly without going through expensive RO process. So if you can bring up a new catalyst that can break down sodium saline in water, seawater, that will be a great development. Storage side, we are looking at cryogenic material behavior, because if you want to store hydrogen in a liquid form, you need to reduce the temperature significantly. So cryogenic research is one of the area there. We need to understand permeation of hydrogen through metal and develop barrier to permeation. So that's another challenge, because hydrogen embrittlement happen in steel. So if you can develop some permeation barrier. Uh, Heat recovery is another research area, because when you are dealing with hydrogen production, a lot of electricity is wasted into heat. So if you can recover that heat, we can increase the efficiency to 100%. Uh, what are the other one? Ammonia production is another alternative fuel area. If you want to use hydrogen as a combustion product, then you need to understand how the combustion work when you blend hydrogen. Some of the other cross-cutting issues include hydrogen sensor development. As you said, if there is a leakage, we cannot detect it. So you need to develop some sensors to do that. We also need to work on society and societal aspect and the safety. You have to convince people that hydrogen is safe. So human perception of hydrogen is very important, and acceptability of hydrogen technology is also very important. So these are some of the cross-cutting issues that we need to look at in terms of research area. And whole system approach. So if you really need to get hydrogen economy going, we have to look at whole system. So that means wind farm electrolysis, solar electrolysis, nuclear electrolysis, carbon capture and storage, gas, coal gasification, biomass gasification, storage, transport, and then utilization, either in the transport sector, pumping station and things like that, or heating your building or commercial heating, whether you can use hydrogen for heating purposes or cooking purposes and things like that. And if you want to use hydrogen, whether that system will be centralized or decentralized or distributed to remote area. So hydrogen across the whole system approach will be another interesting research area, and life cycle analysis of any of the technology is another important research area. So if you go back to green hydrogen again, to develop a green hydrogen supply chain, what you need to do? We need to have a source of renewable energy. Number one, we need to have water supply and electrolyzer. These three things is a must. Then for storage, we need compressor, we need storage tank, we need to have some source of transport, either storage tank transported by truck or pipeline. We also need refueling stations. If you want to use hydrogen in a car or bus, then you need a refueling station, and then you have to think about who are the end users, how you are going to use hydrogen. Either it's for combustion, it's for heating, it's for fuel cell electricity generation, and what type of uses we have at the end user level, that we also need to think about. Only then we can develop whole supply chain of green hydrogen. So we have a lot of challenges still to overcome. First of all, you need to overcome technological challenges. You have to make improved efficiency of electrolyzer. Current electrolyzer is very expensive, so we have to do continuous research to use less expensive material to produce electrolyzer. We need renewable energy source and reliable energy source. So you have to produce hydrogen. So you have to have hydrogen production facility next to renewable energy sources. Otherwise, that will not work. If you have renewable energy sources in one area and hydrogen production facilities in another area, these two will not couple together very nicely. We need to have robust infrastructure for storage, transport, and distribution. Cost effectiveness and competitiveness is a number one area of research. Otherwise, if it is not cost effective, competitive, technology will not be taken up. So supply chain management is again a crucial issue, because a lot of those expensive material for electrolyzer is actually happens to be available in countries where these are political instability and things like that. Okay, now a little bit about water for hydrogen, how we can get water. So if you want to use electrolysis, you see, if you want to use tap water, which is clean, relatively clean, we need 15.2 liter of uh, water. You go through a pre-treatment process, you get a deionized water, 10 liter, and then you put it in electrolysis, you get 1 kg of hydrogen and little bit of blow down of water. In this case, you are using slightly above just 1 liter excess water. Sometime electrolysis process we actually use up to 10 liter excess of water to run the electrolysis process. And also electrolyzer needed to be cooled, so you need again some water to cool down this electrolyzer. If you have 19.5 liter of water in your cooling system, up to 14.6 liter of water is actually evaporated during the cooling, and you get back only 4.9 liter of water back. So you need to put makeup water again, unless you evaporator water you can capture again in cooling tower and things like that. So water requirement is a massive uh, for green hydrogen production. If you use for example river water, you have to treat it, so you need 17.2 liter. If you use groundwater, you again need 17.2 liter. If you want to use seawater, you need 28.6 liter, because seawater 50% efficient. 50% of the seawater is very heavy brine water. You have to discharge back, and you get 50% free fresh, I think, water from RO system. So water is an important thing. And if you think about how the water requirement changes with efficiency, if you increase over the years, the efficiency of electrolyzer is going up, and water requirement actually comes down. So you need to have an electrolyzer which is highly efficient to reduce the amount of water uses in your electrolyzer system. So where we can find water, and what will be the strategy for water uses? First of all, you have to use green hydrogen project, which actually use less amount of water. If you think about other process of hydrogen production, especially methane steam reforming or biomass reforming, it needs some more water than green hydrogen production. And you have to select more efficient electrolyzer, because most efficient electrolyzer you use less amount of water, something like PEM electrolyzer. You have to do impact of risk assessment. So if you want to build a green hydrogen plant, you really need to look at water related impact and risk assessment, and you need to have a very stringent water use regulation and monitoring system, so you don't waste water. And also, if you think about cooling, we talked about, and these are mostly water cooled. Most of the electrolyzer is actually water cooled now, and we need to have a policy maker insist on air cooled electrolyzer. So if you want to buy electrolyzer, if you put a tender out, you insist on having electrolyzer which is air cooled. So that way you can reduce lot of water uses. And also you can look for alternative water sources, something like groundwater, formation water. If you have a oil and gas industry, then produced water you can look at, or wastewater from municipality that you can be used. But those every of these water actually need further treatment, deionization before you can use it in electrolyzer. So water is a big challenge, and many of these countries, if you have lot of solar energy where you can get free photovoltaic electricity, and you're supposed to produce hydrogen from that electricity, but water is a big challenge for these countries also. Okay, so looks at some number now. How much it costs to buy 1 megawatt of electrolyzer? The price is approximately 1.5 million pound. Very expensive. How much is water requirement for 1 megawatt of electrolyzer? So 1 megawatt of electrolyzer, if you run it for 6 hours per day, you need 2,400 liter of water per day, because 1 kg of water need 20 liter of water, and 1 megawatt of electrolyzer, if you run 1 hour, it need 400 liter of water. Okay, so these are the number. If you have 1 megawatt electrolyzer running for 6 hours, you need substantial amount of water. Okay, now you look at hydrogen uses for transport. Little bit of looking at transport. In UK, what is the current transport situation in the UK? In 2022, 112.5 metric ton of carbon dioxide was released due to transport only, and that, which is 34% of the all carbon dioxide emission from UK. So in a transport, UK release one roughly one third of the carbon dioxide emission or greenhouse gas emission comes from transport. So let's look at the transport situation here. This point is Glasgow, one of the big city in Scotland, and this is London. If you want to travel between Glasgow and London, which is maybe roughly 600 mile, I think, how much carbon dioxide is released for one single journey? So if you travel by plane, so traveling by plane is the easiest way, and I think it's a cheaper way also, because we have very cheap flight between Glasgow and Aberdeen, Glasgow and London. In that case, you release 175 kg of carbon dioxide equivalent by plane travel. By motorbike, 92. Of course, it's very difficult to travel by motorbike this amount of distance. Then petrol car, people do that. It's a 90 kg carbon dioxide emission. Diesel car again 90. Train is cheaper option in terms of carbon dioxide emission, which is 28. Electric car 29. That electric car emission actually coming indirectly. You don't have direct emission of electric car obviously, but you have indirect emission because of the electricity you're using may not be 100% green. The battery you use and things like that created a lot of carbon emission in its footpath. And then traveling by coach is the cheapest option in terms of carbon dioxide release. This is a long distance travel from Glasgow to Aberdeen. If you think about travel inside London, there is a place called Croydon and there is a place called Wimbledon. So it's a very nearby place. If you travel between these two distance, if you travel by black cab, which is running on a diesel, you released most amount of carbon dioxide, which is 3.1 kg carbon dioxide for per journey per passenger, a single passenger we are assuming. If you travel more motorbike, it's 1.7. If you travel by petrol car, 1.7. If you travel by diesel car, it's 1.7. So these three are almost same. Local London bus 1.2, because you are sharing the travel with a lot of other people. Electric car again 0.5 uh, kg carbon dioxide emission. That's good, but these are the indirect, not the direct. And then tram is the cheapest option. Tram is the cheapest option. You use 0.4 kg of carbon dioxide emission. So these are the transport situation. You can think about when you're traveling, which type of transport can give you low emission. Okay. Now, if you look at energy sector, energy uses in different sector in UK, so it's roughly one third of input goes into electricity generation. Carbon dioxide emission happens due to electricity generation. One third is transport. One third is home heating, because it's a cold country. You have to heat the home during winter time, and most of the year is actually very cold, so you have to heat houses using natural gas. So in terms of carbon dioxide emission for energy generation, you can see is significantly reduced over the year, because most of the electricity in UK we can produce from offshore wind. Many of the days in Scotland, 100% of electricity is produced from offshore wind. Okay, wind energy is very big. So emission due to energy production came down significantly. If you look at transport, including international travel, you can see it's actually going up. Carbon dioxide emission is going up, up, up. There is a certain dip here. From this point, there is a sudden dip, and this is going up here. Do you know this reason for this dip here is due to COVID? When there was a COVID attack in 2019, so all was under lockdown, so travel actually got down significantly in this time, emission due to, and then it's going up again. So transport is one area where decarbonizing is a big challenge. Energy production, not a big problem. We have managed to reduce it significantly. So transport is a big challenge. How you can decarbonize transport? So what's the whole idea in the UK? By 2030, no new diesel and petrol car will be sold, and van will be phased out by 2030. And you cannot sell any new car and van which has to be 100% zero emission at the tailpipe by 2035. Actually, this used to be 2030, then it went up to 2035. It will be bring back to 2030 again. So all new cars and vans to be 100% zero emission at the tailpipe by 2030. So what's the situation? Main idea is to use electrical car. So we have 68,273 charging point in UK, and we have this amount of car running around in UK. And by 2030, we have more than 300,000 of charging point. So what is the role of hydrogen in decarbonizing? Hydrogen, if you, instead of a electric battery, if you put a fuel cell and electric motor, you have got a lot of advantage. First of all, you can have a longer range, because EV car range is not that long, especially the car we have here, maybe 300 mile or something like that. But hydrogen car can have a longer range. Number one. Number two, refueling. Hydrogen refueling takes few seconds, where electrical car charging may take long time. And also, if you have an electric vehicle, there is a peak demand of electricity grid, especially in the evening, where everybody goes home and plug in their electric car into the network. So there is a peak surge in demand for electrical charging. And of course, electrical battery also need rare materials. Okay, lithium ion and things like that. However, this government policy I'm quoting. So if you want to achieve net zero in transport, they are policing on transitioning to EV is central to government's net zero commitment. So hydrogen, transforming into hydrogen car is not a main priority for the UK government. So if you look at hydrogen fuel cell vehicle compared to electrical vehicle, fuel cell vehicle, this is the chart. Number of fuel cell vehicle in the world actually going up year on year. By 2020, this is the number of car available in the market, not used in the market in our country. The fuel cell is most popular in fuel cell car is very popular in South Korea, is the leading country, then Japan, then you have USA. In between, you have Germany, and then China. These are the major countries using fuel cell vehicle. Fuel cell, not electrical vehicle, fuel cell vehicle. Uh, for the time being, EV is leading electrical vehicle in terms of personal vehicle market because it's cost competitive still. We have the support structure for EV. There are a lot of charging point. We don't have any refueling station for hydrogen, not now. And battery technology is actually making swift advancement. Is going up tremendously. So fuel cell vehicle has a limited market expansion for the time being. If you look at in the map, so if you think about fuel cell refueling, hydrogen fuel cell refueling station compared to charging point, electrical charging point, you can see those are in numbers in less than 100. So this country has got 101, France has got 141 uh, 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 hydrogen refueling station, UK has got 20 refueling station, Spain has got 6, and number not no many countries have nothing. Whereas if you look at electrical charging point at public places is in thousands, and Germany has got more than 50,000. Okay, so comparing hydrogen fuel cell vehicle compared to EV vehicle, it looks like EV vehicle is winning in this market sector, but it can change again in future. uh, However, in Aberdeen, in our town, we have number of fuel cell bus running around for more than 10 years. These are running successfully. Though the bus is expensive, but is people are now got used to using hydrogen bus inside the town. Advantage of hydrogen bus is that it only takes 10 minutes to refuel a bus, and it can deliver 350 kilometer of distance. And another advantage of hydrogen fuel cell bus is that you can fill it up at night and then you can use it. So fuel cell has got a lot of advantage for bus, for heavy vehicle, for train, for ship, where you cannot use electrical battery to quickly charge it, or if you think about the distance travel, you cannot electrify those type of transport. Even plane, you can use liquid hydrogen to run a uh, to fly a plane, but it's difficult to use battery for a long distance travel in a plane. So hydrogen has a lot of use in transport, but for personal car, it looks like electric vehicle is uh, way ahead. So in order to implement a green hydrogen technology, what you need to do? What we need to do? We need to do a lot of things. First of all, you have to have a strategy and target. For UK, we have a green hydrogen production of 5 gigawatt by 2050. That's one target. We need investment. For example, UK government is putting 180 billion by 2050 uh, through various instruments: so investment bank, innovation fund, research and development fund, pure research funding, uh, upskilling fund. So a lot of different source of funding is available for hydrogen. You have to develop infrastructure, that is pipeline. Either you repurpose the pipeline or build new pipeline. You have to have blending system, refueling station. You need to have port for import and export of hydrogen. So you have to redesign your port also. Research and innovation is number one. You need new technology which lead to reduce cost, improve efficiency, and university industry collaboration. We need to have a favorable policy and regulation. For example, if can subsidize fuel cell vehicle, you can subsidize refueling station, you can give tax incentives, you can give subsidies to buy car and things like that. International collaboration and knowledge share is a must. We need to have joint research. We need to have sharing knowledge. That the thing we are doing today is actually very important in terms of making our uh, uh, objective of getting hydrogen economy going through collaborative and joint research. Education and workforce development is again very important. We need to have short courses, we need to have skills based course, and we need to have dedicated MSc course, or even PhD level research. PhD level research is going on for a long time, but we now need courses at MSc level and short courses and things like that. We need to have public awareness and acceptance. That means we need to have workshop, seminar. We need to co-create many of our research program or project. We need to co-deliver many of the research program and project with public, and getting public in confidence of hydrogen. Okay, it's nothing to be fear of when we are using hydrogen in our home for cooking, or in our car for driving car, or even electricity generation. Okay, so at this system, I will thank for your attention, and then in the next step, I will move on to some of the research that we have been doing at our university on hydrogen. I will show you three research and research uh, outcome from our work on hydrogen in maybe next 5 minutes. Okay, so I will again give a break of maybe 5 minutes, and we reconvene 5 minutes. Is that okay? And if you have any question at this stage, I'm happy to.
Yes, Professor. After the questions, we can take some 5 minutes. Then we can take the next session. That will be okay.
Okay, thank you.
Participants,
Okay.
if you have questions, please you can have interact with our resource person from UK.
Yes, somebody has a question. Kanchan Power. You can ask the question directly, or you can put in
Hello.
the chat. Yeah,
Yes, sir. Am I audible to you?
I can hear you.
You can
Yes.
introduce yourself with switch on your camera, please. It will be the live interactions.
Yes, sir. My name is Kanchan Pawar. I'm from Institute of Chemical Technology, Mumbai. I am a PhD student.
Yes.
Yes, my sir question is regarding photoelectrocatalytic hydrogen generation.
Yeah.
So, as we are moving towards the electrocatalytic hydrogen and photoelectrocatalytic hydrogen generation is a new area of research. So, there is a like it is not exactly new. There is a more than 2 decades are over in the PEC water splitting or hydrogen generation. So, can we go towards the scalability or it is possible in PEC generation?
It is possible. Yes, yes. As you say, the technology is not new. What we need is that a lot of the technology is not new, to be honest. It's just coming back and becoming more important. Why it's becoming more important? That we can move this technology from your lab into demonstration and production. So that's the key thing, is the scaling up. In order to scale up, you need to look at how we can reduce the cost. Okay, so if you are thinking your research is inside your lab, and photocatalytic electrolysis is possible, and we have uh, type of electrolyzer that can do that directly. uh, However, you have to think about how cost it is, how efficient it is, whether you can improve the efficiency, and whether you can scale it up at a cost-effective way. So the research will be on those areas, and also, of course, technology development, because the technology is there for a long time. So your focus has to be, okay, we have this technology, how we can make it more uh, 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 improve efficiency, number one, and that will lead to cost reduction. And then wider application. So scale it up, basically. Am
Thank you
I
so
clear?
much, sir.
Yeah. So we, not me, but one of my colleagues is actually working on photocatalytic electrolysis uh, in our university, and he's using that concept to produce actually sustainable aeronautical fuel.
Okay, sir. Can I ask one more question?
Of course.
Yes, sir. So many people I do so many people use electrolyte like whole scavenger and something to enhance the performance, and so many people do research in neutral medium like So do we like need to focus on whole scavenger, something like that? Can we call it that actual performance of HER in terms of current density?
Say again. I didn't get it.
Hello, sir. Yes,
Yeah. Can you
yes, sir.
repeat
I
the
can
question,
repeat.
please?
Am I audible to you?
Yes, I am.
Yes.
Yes,
Sir,
yes,
actually, my question is regarding the electrolyte. So many people use whole
yes,
scavenger and so many things in the electrolyte. Then they get like maximum current density. Okay, if you are
yes.
talking about the current density, but there are reports like the people who are doing in neutral medium, neutral electrolyte, they are not getting that much of current density. So we need
Yeah.
to focus on efficiency, current density, or the like basic stuff.
Okay. I mean, from the commercialization point of view, at the end of the day, you need more hydrogen production. Okay, and more hydrogen will come from higher current density. Okay, so you can bring in a new technology, as you said, but you are not getting the current density that you want. So you have to do continuous research to improve the current density.
Okay, sir. Thank you so
Yeah.
much.
Yes. So in terms of, if you look at the basic principle of electrochemistry, where are the losses happening? One is the activation loss, one is the resistance loss, and one is the flow dynamic loss or concentration loss, right? So, so
Yes,
now
sir.
you have to think about where you can make improvement in terms of reducing these losses. One of the loss is actually electrical resistance kind of loss. So you have to focus, and that is inherent to material property. So you have to make electrolyte maybe thinner, but you cannot make it lot less. I mean, there is a limit how much thin you can make, and so that's one challenge. Another challenge is how we can make hydrogen to move around quickly through porous material, and so you can then improve the concentration over potential and things like that. So you have to look at what is the challenges and how you can improve them. Another way is to look at is, if you look at electrode, many of the electrode design is not efficient because maybe we are putting this material in deep coating or thermal spray coating or things like that. I will talk about this later, but not all the uh, electrode is used in electrochemistry. Some of those material may be wasted because these are complex structures. So whether we can, uh, from the material science of material point of view, whether you can improve the microstructure of the material, and that will give you better electrochemistry, that we can also need to do a lot of research, fundamental research. So fundamental research is very, very important. You cannot get away with fundamental research, but then we have to think after the fundamental research how we can improve the efficiency. Okay, you have another follow-up questions, Kanchan?
Yes, sir. Thank you so much. So, as per fundamental question, so fundamental, we need to focus on like the uh, heterojunction type of thing or Z scheme which can enhance the property of our material.
Yes, of course. Because now another way to think about it is that what is our role as a university? Our role as a university is to do fundamental research, but at the same time, a lot of our research is funded by the public fund. So we have a commitment to public fund. So we have to make sure our research then lead into some application and some good to the society at the end of the day.
Thank you so much, sir.
Thank you. Any question? I think somebody raised hand. Or...
Professor, yeah, Mr. Ankur Sachadev, please you can.
Yes, please.
Hello. Hello.
Yes,
Am I
proceed.
audible, sir?
Yes, I can hear you.
Am I audible, sir?
You are
Yes.
audible, sir, please.
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, my question is, can hydrogen also play a role in, since I am a research scholar in refrigeration and air conditioning, so can hydrogen also play a role in the refrigeration and air conditioning applications?
It's not directly, But indirectly, if you are working on refrigeration, you can think about how you can use uh, your refrigeration technique to liquefy hydrogen. So you have to go
But
down
then,
and
sir, it will be cryogenic application only.
cryogenic application, yeah. So for storage, because we have to, some of the storage has to be liquefied hydrogen. Yeah, we
So,
cannot
sir,
have.
can can we use the, sir, electricity generated by the hydrogen in the running the compressors?
Oh yeah, yeah. Of course, you can do that. Yeah, that's the application of. I mean, as you said, hydrogen is just a fuel cell is just a battery, DC battery, DC current it produces. Okay, so it's very similar to a battery. You can use it anywhere. It had a wide range of uses.
Okay, sir. Thank you.
Okay. Yeah. So, if you think about research area, uh, what I would say, there are a lot of scope for uh, different areas of research. First of all, is a fundamental research. Those who are doing material science, they may be looking at structure of catalyst and electrolyte, especially catalyst. Then those who are doing electrochemistry research, they may improve electrochemical process of the uh, electrolysis process. Okay. Those who are doing fluid dynamics, they also have a role in hydrogen production, because you have to make fluid to flow into electrolyzer, and you have to make the fluid to flow out of the electrolyzer. Those who are doing like a compressor research, as I said, they have to look at how they can develop compressor for hydrogen compression, because this density is so low for hydrogen. You need to start off with a bigger compression at the inlet, and then subsequently probably reduce it. So compressor research who are doing, they also need to look at how they can develop compressor. A heat exchanger is another area. Those who are doing heat exchange or heat transfer research, there are a lot of thermal management issue in electrolyzer and hydrogen production and waste heat recovery. So heat exchanger designer, they can look at it. Those who are looking at phase change material, they also have some implication in balancing temperature within electrolyzer or fuel cell using phase change material and things like that. So a lot of, and those who are looking at kind of a applied research, maybe you can think about use of fuel cell or hydrogen in many different innovative way, like bicycle. A lot of electrical bike is coming up in market. So instead of electrical battery, whether you can have hydrogen fuel cell uh, uh, in your bike, and if you have scooter or CNG or tuk-tuk, whatever you call it, whether you can blend some of the hydrogen into their existing uh, combustion chamber, two-stroke or four-stroke combustion chamber, and then uh, use those to decarbonize a little bit, not 100%. Maybe you can blend hydrogen up to 20% without changing any infrastructure. Okay, so these are the type of research, lot of research you can do in different area of hydrogen. This is not only one area, but is a wide range of areas you can focus on. So you can think about what expertise you have, because hydrogen is a new area. So you think about what expertise I have, and then I can contribute to which area. Even water treatment, those who are expert in water treatment, they can look at, we can take dirty water, clean it efficiently, economically, and then use it in electrolyzer. Okay, so there are a lot of scope for doing research in hydrogen domain. Okay, so if no question, I can move on to next part of my presentation. If you
Yes.
are all
Excuse me,
okay.
sir.
Hello, sir.
Hello.
Yes.
Sir, can you
Sir.
please give me low cost water treatment process which is we can use
Water
as
treatment
to be other
process.
than
Okay.
reverse osmosis? any other process?
Yeah, it's basically you have to have water. You have to first of all screen it, filter it, right? All of the waste, and then you can then put it through reverse osmosis process, and then you may need to have deionization, and then you put pure water into electrolyzer. Okay? So it's a uh, reverse osmosis, basically reverse osmosis process.
Excuse me, sir.
Yes, please.
Sir, I have a question that we were talking about that the quality of water required before the electrolysis,
Yeah.
right? So, can we have the same process for vapors or steam? That there is one concept also of high temperature electrolysis. So,
Yeah.
instead of that, if we have a closed chamber with the vapors, which is
Yes.
naturally vaporized. So
Yeah.
can we have that same process for this hydrogen production?
So you're using vapor or steam, right? And
Yes.
this is a clean steam. You don't have any other impurity, any other dissolved solid, or any other.
Y- Yes, but even if we talk about steam, so we need to have some thermal equipment for making the steam. But if we have a naturally vaporized water, which some closed container which is full of vapor, so can we have this
How you do
electrolysis
that?
go in
By
open?
reducing pressure or something.
So how that process will work in that case for vapors?
Yeah. So how you evaporate? That I was asking.
So I'm saying that I have a closed container with the
Yeah.
partially filled with water and rest of the space is filled with vapors.
Okay. And at what temperature and what pressure and how much? That will be the challenge, right? For producing 1 kg of hydrogen, we need 10 kg of steam, right?
Okay.
So you can
So
have supply of 10 kg is a
no,
natural
no, sir.
vaporization. Natural.
My question is in that vapor space. So how
Yeah.
we put our electrolysis process?
Yeah, I will tell you in a minute. That's the next step of my research. Okay,
Okay.
presentation. So yeah, after my presentation, you can ask the same question.
Fine, sir.
Okay. So shall I? Can I go ahead, please?
So
Yes,
just suppose,
Professor. Yes, yes.
yeah.
Okay.
So for SOEC electrolysis,
Yes.
how much steam is required to generate 1 kg of hydrogen?
How much steam?
Yes, because the
9
steam
kg.
is a feedstock, right?
9 kg of steam.
Is more or like a similar to alkaline and PEM?
Alkaline. Yes, it's a electrochemistry. If you look at the what do you call uh, it's about steam or water is split into hydrogen and oxygen. So if you look at stoichiometric, yeah, so 1 kg of hydrogen you need 9 kg of water. But to run your system efficiently you put more water, right? It depends on like a PEM electrolyzer you may use 10 kg, solid oxide electrolyzer you may use 11 12 kg in
Yeah,
alkaline.
hardly it requires 11.5 or 12 liters.
Yeah.
Yeah, yeah.
Yes.
But
Yes.
SOEC, the feedstock is the steam and
Yeah.
the superheated steam. We can't say the steam only because its
It's a
compressed
superheated
heat
steam.
is around
Yeah.
500 degrees Celsius.
Yeah. Superheated steam.
Because obviously the quantity can be vary, right?
Yeah.
Yeah, that quantity is it similar to 9 liters?
Oh yes. Yes. It's a 9 liter, but it's a 9 kg. You shall I say, not liter. Okay, because you uh, water turning into steam. But if you look at the stoichiometric chemical reaction, hydrogen is split, water is split into hydrogen and oxygen. So 1 kg of hydrogen need 9 kg of water or steam, whatever form you have.
Okay, fine.
Okay, you look at the equation, basic equation, and you need more because you cannot ensure that the chemical reaction happening on. Always you have either rich or lean combustion. You heard about that, right? More than stoichiometry.
Yeah, because I read about it's around 550 to 900 degrees Celsius. The feedstock is required for
Say
SOEC.
again, five.
550 to 900 degrees Celsius for
Yes,
SOEC.
yes,
Yes,
yes.
then only we can achieve the 90% efficiency, the electrolyzer.
Yes, it's a wide range, isn't it? The
Yeah.
number you are putting is a
If we
wide range
take,
of
yeah,
temperature.
if we take generally normal water, again the additional energy is required to generate the steam. This
Yeah,
is more or less equivalent to alkaline PEM, the
yes,
same energy consumption.
yeah. Alkaline is the liquid. Alkaline is in the advanced stage, but it's in the liquid form. So there is a risk of leakage and things like that. But in China, they are building a lot of big electrolyzer using alkaline electrolysis. Okay,
Okay, sir.
so let's move on. I will take your question again. Now I'm going to talk about some of the research going on at Robert Gordon University. First of all, I'm going to talk about solid oxide electrolyzer development. We have a big team of people working in this area. My colleague Nadimul Faisal, Anil Prathuro, Victoria Kurusina, Vinut Rajendran, Chiang Kai, Bhaman Hori, and Ajit Kumar. Okay, oh, that's a better figure we have. So these are all our team here working on this uh, hydrogen production using solid oxide electrolysis. And the project, we call it METASYS project. Scalable metamaterial thermally spread catalyst coatings for nuclear reactor high temperature steam solid oxide steam electrolysis, METASYS. So we have a team at our university, Robert Gordon University. We are Professor Nadimul Faisal and Professor Mamdud Hussain, that's me. And then we have our junior lecturer, Dr. Anil Prathuru. Two researchers working on this project. One is Dr. Victoria Kurusina. She is here. She is the research fellow. And also Vinut Rajendran, who is a PhD student and research associate in this project. And these are two of my colleagues, as you said, Nadimul Faisal and Anil Prathuru. And this figure has got our team member from University of Surrey, which is Dr. Mahaman Hori here. And I think she is Professor Kiang Kai here, and also researcher Ajit Suman here. Okay, uh, this project is funded by a number of project partners. One is UKRI. We have used ISIS neutron and muon source, National Nuclear Laboratory. They also partnered with us, and Engineering and Physical Sciences Research Council. They also funded this project here. So what we are looking at, and some of your query was before, is why we are looking at high temperature electrolysis. So if you have temperature below 100, you play with liquid water to convert into hydrogen. If you are more than 100 degrees Celsius, you go into high temperature zone. What is the advantage of producing uh, hydrogen at high temperature? That's the overall energy demand. That's the key thing. If you use electrolysis at a high temperature, your total energy demand actually goes up with temperature. So higher the temperature of electrolysis, higher the total energy demand. But the key thing is the type of energy you need. At high temperature, you need less amount of electricity input. You see, electrical energy demand goes down, which is gives energy change, gives free energy. Higher the temperature gives free energy, you need less. That means you need less uh, electrical energy. However, you need more heat to uh, have electrolysis process. So you need heat, higher heat demand, but low electricity. So what is the advantage? Because advantage is here, the price of electricity is high, price of heat is low. Heat energy is cheaper than electricity energy. So if you produce hydrogen at a higher temperature, you need less electricity, more heat. That's the important thing to remember. Okay, so where is this heat coming from? We can get heat from geothermal source. So one idea is to look at if you have geothermal source. So you can get, if you go to say 1000 meter, 3000 meter, or 5000 meter deep, we can get a temperature of 40 degrees Celsius, 90 degrees Celsius, or up to 150 degrees Celsius. It's not a lot, but it's still there is heat coming from geothermal energy. Another way to look at, we can get lot of waste heat from different sources. Uh, However, with this geothermal energy, we can produce electricity. We can also use heat pump to increase this temperature to higher temperature, is possible. However, other way to look at this in UK is there are a lot of heat is wasted, waste heat. So in the electrical generation process, we use lot of heat. Different processes, we waste a lot of heat. And the place we are here in Aberdeen, where place is here, we also have lot of waste heat around this area here. Okay, total waste heat 390 terawatt hour. In industry is 46,000 gigawatt hour of waste heat, and in electricity generation we have 345 gigawatt of heat. And heat is cheaper than electricity, as I said, but difficult to hold. The challenge is how you transfer heat, how you keep hold of the heat. Okay, so another heat source could be a nuclear plant. So in a nuclear plant, 60% of the waste heat is there. Nuclear plant also have excess electricity. So in UK, we have number of nuclear plant around the country. Some of them are in the decommissioning phase. Some of the one are very new. These are Hartlepool, Hissam, and Wilfa here. These are the confirmed new site. The red is already in production. So there is two in Scotland, Torness and Hunterstone and things like that. And some are closing down, of course. And this nuclear plant has got a lot of good heat available, steam, superheated steam, as you said, high temperature steam coming around 600 degrees Celsius or 650 degrees Celsius, or slightly less than that also. But there is a heat there. And so the idea is to use that waste heat and renewable electricity to produce solid oxide electrolyzer. So this is again a schematic drawing of a kind of a nuclear plant. You have steam generated here. It goes to steam turbine, come back. But we can bleed some of the steam from the steam line and take it out. We actually don't use directly this steam. Rather, we have a heat exchanger when we pass through this system through another secondary heat exchanger to transfer heat into this electrolysis process. Okay, so how does this electrolyzer work? I will explain to that in a minute, but before that, there are some number to think about electrolysis process. In UK, there is a target of producing 10 gigawatt of low carbon hydrogen by 2030 using electrolysis, and also a target of 75 gigawatt of minimum renewable power will be connected to the grid to achieve net zero target in 2050. Nuclear sector, there is ambition produce from the nuclear sector 75 terawatt hour of hydrogen by 2050. So if you look at different technology of electrolyzer, alkaline is well ahead in terms of development, and then PEM and solid oxide electrolyzer is in the lab phase. It's not many in commercial phase actually. One of the important thing is actually what we are talking about is total waste heat available in UK is a substantial amount, and that we can use it for electrolysis process. Current hydrogen projection cost from nuclear power and waste heat is about 2.79 to 5.74 pound per kg. We need to bring it down to 1. That's the target, 1. So according to UK NLL, that's a National Nuclear Laboratory, they estimate that they can reduce the price to 1.2 kg to 2.2 pound per kg steam electrolysis coupled with nuclear plant and things like that. So there is a scope for coupling electrolysis with nuclear plant to reduce price of electrolysis. So let's go back to our work, what we have been doing. So in a solid oxide electrolyzer, we need basically three main elements. We need a cathode, we need electrolyte, we need anode. Cathode is made of one type of material, electrolyte has another function, another type of material, and anode is another type of material. How it works, a, you pass the stream through cathode. In a cathode, you also put a electricity supply. You put some electron into cathode. What will happen is your hydrogen, sorry, your water in the steam form will break down into, this is your water. You have an oxygen, two hydrogen, H2O is split into hydrogen and hydrogen. So we have a hydrogen combined together to create a hydrogen gas, and we are left with a oxygen ion because oxygen is fed into two electron. So oxygen becoming oxygen ion here. This oxygen ion then only can flow through electrolyte. This electrolyte here is only allow oxygen ion to flow through. It blocks hydrogen, it blocks steam to go through and electron to go through. So oxygen ion flow through electrolyte to the other side. In the other side, it gives up its electron to the electric circuit here and become oxygen gas again. So in the anode, we getting oxygen gas. Before it became oxygen gas, it was in an ion form, and that ion was created in cathode, and oxygen ion flow through electrolyte into the anode side. And so we need a electrical circuit which is bring electron from anode and into cathode. And in the cathode, it gives electron to split water into hydrogen and oxygen. Oxygen take the electron, it becomes oxygen ion, and ion flows through electrolyte into the anode section. So that's the whole thing. So what you need is a cathode, electrolyte, anode. Okay, so let's look at first generation of electrolyte here. What we have? We have a thick cathode here, then electrolyte, then anode. And if you look at the type of material used, mainly use nickel and OSZ in the cathode side. Nickel and OSZ in the cathode side. In middle part here, which is electrolyte, we use OSZ because OSZ is good for ion conductivity. It doesn't allow any other material to flow through except ion, and is a dense. It doesn't have any porosity. This side has got porous material, which is made of nickel and OSZ. Nickel and OSZ, which is a porous material, which allow steam to flow through these gaps into uh, what you call a triple phase point where electrochemical reaction takes place. We need to have some mechanism to flow electron. Electron actually flow through nickel, and OSZ allow ion to flow through. So that's why you have nickel and ion, and you have uh, this gap for steam to flow through and hydrogen to come out. Then, as I said, OSZ only allow oxygen ion to flow to the other side. Other side we have LSF or LSM or LCF, and those are also good material to allow uh, uh, oxygen ion to flow through and also combine electron uh, releasing making electron to flow through taking electron out from oxygen. So those are sometimes we can have dual conductivity of electron and ion both in the same material. And we need a current collector here, which can allow electron to come and then release electron to other side, a current collector here. So this is the old system, 3 structure. Now we invented our structure is that we need a support material. So we put a support first. Support material is made of porous stainless steel to give you the strength, because it's working at a high temperature and sometimes high pressure also. So we had a support material first. On top of support material, we put a current collector, which is AG. Then we put a interconnector layer to make this current to flow, AG nickel oxide thin film 10 micron. Then we have nickel oxide and GDC material with a porosity of 30 to 40%. Then we create a dense electrolyte made of GDC and YSJ, 2 layer, multiple layer. Uh, so, and then we have porous anode with a GDC LSCF, porosity of 30 to 40%, thickness is 40 to 50 micron. So our advantage is that initially this type of strength they used to have 400 500 micron, because that provided the support. Now our structure has got stainless steel as a support material, and we can now have electrolyte which is very thin. We can have uh, anode and cathode which are very thin, because all is supported on our substrate, a uh, porous tube made of stainless steel. So we can reduce that electrical resistance that I talked about in answering one of the question. We can make it thinner to reduce uh, uh, what you call a electrical resistance. So our thickness is actually 2 micron, 3 micron, 5 micron, 40 to 50 micron. We don't need 400, 500 micron or 1 millimeter thick cathode and anode anymore, because these are all supported on that structure. Number one. Number two, we have a balance of porosity, and we have multi-layered cathode, multi-layered anode, which is made of nickel oxide GDC, then GDC, then YSJ. So you have different combination of electrolyte and cathode material. Some of the cases we also had another layer of nickel oxide with OSJ and things like that. Okay, so we played with different multi-layer structure, different porosity, different thickness, but our advantage is that we put it everything on a support structure. Okay, so what are the material we bought? We bought nickel oxide GDC, slurry here, nickel YSJ again slurry, YSJ slurry, GDC, LSF GDC. We mix it up. We went through a lot of ball milling and this and that system. Then we looked at powder material. We looked at microstructure to give us some sense of ideas what type of material we are dealing with, and then we started layering on top of each other. So we have uh, our tube, then we have silver, one is stainless steel, and titanium. We use 2 different tube, one is stainless steel, one is titanium. These are all porous. This is our base structure that doesn't take into action in electrochemistry. It's just a support. On top of that, we need to put silver, because that is a current collector. Then we put deep coating of slurry, cathode functional layer. We build up one layer after another layer and after another layer on top of each other. So you can see 3 different layer here, because we didn't do coating 100%. So this is our cathode is export. This is our anode, which is also export. So we can have a current with this surface and with this surface. Okay, so this 2 layer is, and we are did it with dip coating here. We are doing it by hand, dip coating, and then we have to do sintering, and also we mixed up the slurries in ultrasonicated slurries, and high temperature sintering. These are the process we did. So ended up with uh, this type of tube. We also use some thermally spread cathode and anode layer deposition. So in our lab, we did deep coating, and we also send out this tube to a external company. They did uh, thermally spread, and we wanted to look at which process gives you more stability. So again, self fabrication, we are gradually have silver, stainless steel, silver deposited, sintered, then we nickel YSZ coated and sintered, another layer YSZ and GDC, one coat and another coat, and finally ALSCF YSZ coated. Okay, so you are building up from uh, from our tube into building up different layer on top of each other to create our electrolyzer. Okay, so once we get the electrolyzer, we of course make cathode and anode and make electricity to flow. So that's our outer side is anode, our inner side is cathode. As I said, we expose the end. We always keep the end exposed so we can connect. This is our cathode, this is our anode, so we can simply connect electrical connection wiring. Very simple setup actually, hand on top, things like that. We also did characterization. We put it through SEM and things. Look at how those different material deposited on top of each other, and we measure the thickness. Our design, say we are saying we are looking for 14 micron, 40 micron, or 50 micron. So whether we are getting that. Electrolyte average 8 micron, cathode is average 112 micron. So cathode become actually quite. We wanted to have a smaller cathode, about 30 to 40 micron thickness. However, it turned up 112 micron average cathode depth. So we have to optimize this. This is stainless steel. On top of that, we are putting cathode material, then electrolyte, and then anode. Anode was okay. Electrolyte okay. Cathode become deeper. So we have to look at how we can optimize this deep coating system. How long we need to deep it, how long we need to sinter, and things like that. Okay, so we did this type of okay. So as I said, main losses, if you look at fundamental theory, again, main loss is activation loss, which is due to electrochemistry reaction. We have ohmic loss, which is due to electricity resistance. So we have to make this thinner basically. And also we need to have a uh, we need to have make sure that steam, hydrogen, those are flow nicely in and out through porous material. Okay, and higher temperature, as I said, lead to. Uh, so this is our system, which is 200-watt system. We have a very small system that we developed, 200 watt, and this is our experimental setup. So our objective is to improve efficiency, lower cost, durability, scalability, and system integration. So we are looking at all of those to head up. So this is our system here. We have a water tank, we have a metering pump, water goes in, we generate evaporator mixture here, we evaporated here, and then it goes into the system. We have a furnace and we heat it up to desired temperature here. So it's not a superheated steam, what you are calling about before. We are not generating steam, we are evaporating evaporated mixture here. And that's
Hello. So, Professor, I think it's sessions is over. Then let me start my last sessions. So we like to give thank or we are about to join. So give me some 5 minutes. So about to confirm it, sir. So good evening, sir. Good evening, all of you. I hope I'm audible to you all.
Yes.
Connect. Before that, I like to share the last session, the last session, session 13th. Yeah. I think my screen is visible now.
Yes, sir. Yes, sir.
Thank you.
Sir,
Yes.
press F5 for slideshow.
Okay. So good evening, Unanda. So it's the last sessions, so session 13. Before that, I'd like to thank Professor Mahmood Hussain, who joined from UK. So on is in 4 hours back for Indian time, almost 12 o'clock. We might be having in the morning to since from he started his morning and having a talk about a lot of insight information about. And carbon neutralizations and what you call it, and what is the research work which is happening in this their university. So it was very informative, and I like to also what you call it and thank on behalf of our university side. So for his time and spending with us and sharing his information. Probably someone might be having an interest to do collaborative research with him. Please, we can have communication by email. So we will share all the resource person contact details, all the participant contact details to you once the program is over, along with the recorded video. So that's what I like to say here. So my screen is visible now. So let me start my lecture to the session of the 13th. Yesterday, I did not share some of the basic details about this thermoelectric generator, where the solar and thermoelectric, which is combination of generating electricity to drive this electrolysis. That's what we are making a component of thermoelectric, how it is going to be work on this performance enhancement. My second slide. So how to go for what you call it in slide show? I think it's
Press F5, sir.
is it okay?
Press
Yes.
F5 for slideshow.
F5 for slideshow.
F5, F5. On the key.
1 minute. F5. Connected for F5. I think it's visible now. No.
F5, sir.
Okay. Fine. Yes. No. Is it visible? No. No, no. Could you, any participants, I think, would you help me out to
Yeah, it is from slide show.
this slide too, but I want to go for what you call the 10 slide.
Show.
So,
Slide show. It is insert, draw, design, animation, then slide show.
insert.
Yeah, insert after that. It is
Top.
yeah. It is slide insert, draw, after that design, and after that it is slide show. Next to this one. Next.
Next one, sir.
This one. Yeah, from current slide.
Slide show, sir.
Is it visible now? No.
Still not. I think today again the same problem. You are not sharing the entire screen.
Okay. I am sharing an entire screen only. Let me reconnect. Okay, you are asking entire screen. Now,
Yes, yes.
it's visible now. Yeah.
So press the slide show, sir.
Yeah.
Yes.
Now
Yeah, definitely, sir.
Thank you. So thank you, participants. So it is my session, the lecture 2 on this session 13th. So again, the continuation of the last sessions. Some of the things I could not, what you call it, synchronize in a way, so that I'm doing it here now. I like to give some introduction, then thermoelectric generator. That's what I mentioned in thermoelectric generator, solar thermoelectric generator with a flexible phase, flexible phase change materials. Then improvement of further research work and some conclusion and references here with an acknowledgement. The demand for the clean energy resources, a great concern in the last 2 decades. So since in the reduction of use of fossil fuels for developing more cost-effective renewable energy technology has been demanded more and more. The solar energy has still some disadvantages, including high upfront cost, the requirement of the large and sunny surface area, and no nighttime functionality. These are some common issues. The direct energy conversion device, which attract researchers and users due to simple in design, construction, and easy to fabricate. The standalone solar energy conversion integrated systems with a thermoelectric and paste change material now changed into the composite paste change material have the potential for cost-effective clean energy devices. Where the PCM, it is a material which is going to absorb, its ability to absorb or release large amount of latent heat at constant temperature. So it is a potential for thermal storage application, the diverse domains, the industrial waste heat recovery, constructions and solar thermal storage. Based on the chemical composition, it can categorized into the organic and inorganic, where this organic PCM have large interest due to their exceptional thermal characteristics, such as high thermal energy density, narrow phase change temperature range, and uniform melting compared to inorganic PCM. The paraffin, it is composed with solid alkanes, demonstrated in organic PCMs. White, it is an odorless, waxy solid with a melting range 47 to 64 degrees centigrade. The high thermal storage capacity, it is in 240 joules per to joules per gram. The low toxicity, excellent biocompatibility, and thermal stability, a subject of significant research interest. It is a critical limitations. It is a low thermal conductivity and potential for heat leakage. The heat leakage can be avoided using that composite paste change material. So that's now that conversion of solar radiation into electricity, it is an indirect method and direct method, where the direct method, photovoltaic panel and thermoelectric generator, can be preferred to use a small scale unit less than 1 kilowatt. Photovoltaic panel are limiting the users due to the higher cost and low load factors. That is a factor in electrical terminologies which is used. Where the indirect method, it's solar thermal collectors, and it consists of heat exchangers and heat engine cycle, medium and high power capacity more than 10 kilowatt. It is in the range. So where organic Rankine cycle or in a steam Rankine cycle, they used to for in the first indirect method. The conversion of solar radiation into electricity, where the integrated energy system, where the standalone system is integrated with what you call it an other energy system, so we can improve this overall performance. That's and overall efficiency of the system. Where the solar PV panel above, it is in 10% on the outside, in the outdoor experimental efficiency, where the solar Rankine system is less than 15%, this collector is less than 20, where integrated energy system gives better efficiency compared to the standalone systems. Many research work, the people are in outlay a different combination of energy system to develop the cost effective and energy efficient energy conversion systems. Integrated thermoelectric generator incorporated with an existing energy conversion system is a future in the clean energy conversion and the impact on environment image too. The direct energy conversion systems, it is many categories which is available in solar photovoltaic, piezoelectric converters, thermoelectric converters, thermionic converters, thermophotovoltaic converter. What are the silent features which is connected is less loss in conversions and more efficient and reliability, so that is missing, but the less in cost. So thermoelectric conversion technologies, where it is a current thermoelectric conversion efficiency, usually it's too low to compete with the dynamic technological and for the standalone system. The current thermoelectric material, it's a power 8 to 15%, again 25 to 45%. The cooling, it is in COP, it is a coefficient of performance, it is 3 times lower than the typical compressors. Advanced thermoelectric material schools, it is next 3 to 6 years, where in average EJT factor, it's a power factor value. If it is an improved, it's an efficiency, it's going to be better. Where this cooling also, it's going to be improved in 5 times, 2 times to the 5 times. It is an attractive, it's a number of what you call it an applications where so we can integrate it, but the both large scale system and miniature devices. The CFEC effect, which is happening, what do you call it, discovered in 1821 by Thomas CFEC. So where the two semiconductor material which is taken into that consideration, it's hot junction and cold junction, so metal A and metal B, maintaining at 2 different temperatures. So it's going to be EMF is going to be generated, it's going to be measured, where with the help of what you call it an CFEC effect. Where the CFEC effect in the bottom side, probably you might be seen, it's a pictorial view. So where direct thermal to electrical energy is going to be converted here. The thermoelectric models, where it's basic components, how yesterday also we shown some diagrams here. So look at this cold side, it's a flat plate in collectors, flat plate in shape, top side and bottom side. So in between there are sandwiched P and N material semiconductor is sandwiched, it's connected in series by electrically and thermally, which is in parallel. So it is power generators, where it's that's what I said in yesterday. It was what you call it, and if you keep the thermoelectric model at your hand, it's going to generate 20 watts. Where whatever it is 20 watts photovoltaic PV panel, so it is a bigger in size. So that's what in compact in size in the overall. Where this figure of merit value, the mention I pointed out here, the factor, it is Z, which is in the CFEC coefficient value and the thermal conductivity and electrical resistivity value. So where this CFEC coefficient is, which is called, it's a power factor, where there are different thermoelectric materials which is happening, which is existing. It is bismuth telluride, lead telluride, and silicon, germanium, and bismuth antimony. Where the bismuth antimony, which is established at the combination at an IIT Mumbai, where the Department of Physics, where other categories, it is categorized as low temperature, medium temperature, high temperature application. The future is very clear. It is a more reliable, more, it's very silent since there is no moving component. And no moving component, there is no friction. That's what it's an absence of frictions. Where it's a flexible in size, we can add this PV, what do you call it, and PN junction materials more and more. So it is very flexible, and no combustion is happening here. So it is called, it's no emissions. Where this figure of merit value, which was in already established one, so it was happening, what do you call it, and in this small pictures, where it is the figure, it is called as in figure of merit value. It is up to touch 1.4, but that impact which is happening, people are working on with number 2, the figure of merit value. When the figure of merit value, which is going to number, probably the thermoelectric energy conversion efficiency, it's going to lead, what do you call it, in Carnot cycle system efficiency. Where this lithium telluride, so silicon germanium, so lithium telluride, there is an Ta3, Ta3, so it's in high temperature applications. Where silicon germanium, also it's what you call it, an medium temperature application. Where it's a bismuth telluride, it is a low thermal, what you call it, low temperature applications. This efficiency, it's very less. So when, what you call it, compared to other things, where other component lead and telluride, it gives, what you call it, figure of merit value, there is a power factor value, it's 1.4. It gives better efficiency, but it need an operating temperature. That's what yesterday professor is asked us. So what is the operating temperature which is needed? The operating temperature based upon the material, thermoelectric material which is used here. When we are expecting, what you call it, some solar solid particles where 700, more than 700 degree temperature, operating temperature, so we should not use the bismuth telluride. So we have to select the material which is in a lithium telluride. It's going to operate in high temperature applications. So that will produce, what you call it, sufficient reliable power from without any moving component. So where this efficiency terminologies, it was calculated simple correlation equations, where we can also consider, so how that in your thermodynamics, sorry, heat and mass transfer, where the heat sources which is in thermoelectric material, thermal conductivity, so where, what you call it, the temperature difference across, what you call it, sources, where the heat sink, it is also in a similar, where it's a maximum possible heat transfer which is happening, efficiency, we can easily calculate, that's Carnot cycle efficiency. That's what it is, Th minus Tc by Th, where thermoelectric material is having different efficiency terminologies based upon the ZT. So it is called, what you call the thermoelectric material efficiency. It is a Carnot, it is a thermoelectric material efficiency. The best experimentally demonstrated maximum ZT value, its value, it's 1.5 to 2, it's reached. So that value it's going to be reached here. So probably it's this, once if you know the hot side and cold side temperature, this maximum efficiency will reach around 25 to 30% without any hesitations. So this, again, I like to highlight some more things here, where the thermoelectric conversion, where the thermocouples, which in array, which heats applied, the heat rejected using some cooling method. For the cooling only, so we are concentrating some so flexible exchange material. That is a newer version of PCM. And this concept where thermoelectric generator is going to generate only, what you call it, DC current, direct current, but it acts as the thermoelectric device. It's simply in a similar combination act as a cooler, power generator, or thermal energy sensor. So it's on the miniature applications, where it's various applications which is already discussed, where it is in military applications where it's going to be used, or aerospace, and instruments of the biology. Biology, it's what you call it, and the human, the pacemaker. The pacemaker, it's powered by a normal battery, that chemical battery. So once the chemical battery charging capacity is over, the patient also feels what you call uncomfortable, while you can take the battery from you, cutting the body. It's uncomfortable to them. So for that, if you keep this what you call it an implanted thermoelectric model in the human body, the patient's body, whenever the fluid flow or what you call it and blood which is moving in the body, it's going to be generate some amount of temperature gradient that activate these thermoelectric models. So that's what it's a application that's also joined. On the application of medical implantable devices also it's working well. The medicine and industrial or commercial product where it is working very detailed one. So probably this thermoelectric model, someone might be knowing it's how it's going to be work on this component. So it is a fabricated, exploded view of this thermoelectric model and joint view of the thermoelectric model which is happening here. How the size of this thermoelectric leg. So that is most important here. It is a square in length, so where it's a it's almost 0.95 mm. So 1.6 mm, what you call that, in height, where breadth and width it is a 0.95, then height only 1.6, where it can be used here, what you call it, into fabricating, where this what you call it, the middle figure where in a green color which shows what you call it, and it is a copper contact. So copper contact, it is what you call it an electrical conductor, where top side it was used one more metal plate, it is called as an alumina. It's going to conduct only in what you call the thermal energy, not an electrical energy. That's what it's going to be. It's worked in this principle. So overall dimension of the thermoelectric model, that's what yesterday I also mentioned the number. It is a 50 mm, the width and height. So probably you can easily have a look at the exploded view. Then another, it's a cut view of this section. It's clearly mentioned where it is a schematic diagram. So where the top chip, it is at C, it is a cold side, where in the bottom side it is a TH, it is a hot side, where the schematic is shown here. Where the two leads which is connecting in the two end, it's called what you call the output voltage. Where the cold junction, what the hot junctions, probably it is a PN junction materials, where we can easily finding out very easy way. Then the constraint on this what you call the thermoelectric model. So low thermal conductivity, the influence the temperature changes, which reduce the heat storage and the release rate. Where this heat leakage in what you call it in PCM material with the porous media and the micro encapsulating PCM and integrated PCM within the polymer and matrix, which is called as composite paste material. Polymer paste stabilized PCM easy to prepare a desired size. High density, low density polyethylene, linear low density polyethylene, polyurethane, etc. But the high stiffness of the PCM, it's leading to the brittle fractures and also significant contact thermal resistance, reduce the thermal storage efficiency. So then hence we can go for what we call it a flexible patient material, that is called as an olefin block copolymer, OBC. It is called symbol. So it is a thermoplastic elastomer. Then the crystallizable ethylene octone block, it is a hard block, it is used for in mixing with the PCM. So it's also helping its what you call the to improve its thermotropic flexibility and the reversible transient from the flexibility to rigidity when the temperature falls below the melting point. So it is more advantages here. Then combining OBC PCM address the leakage problems and enhance the flexibilities. And that's what we like to present here. Some what you call it test which we examined for an SEM and what you call it an XRT test for our some samples. The materials which adopted what you call it paraffin wax. So it was some typing error. It seems it is on selection of PCM and then selection of polymeric material. It's an OBC we are considered, where it was prepared with 3 samples: the PCM weight basis and PCM and then percentage in grams and copolymer in gram and percentage basis. We taken 3 cases and we made it some what you call the process, how that is in melting and what you call the stirring process and complete melting and continue heating, boring mold and make it some what you call the block and it is tested. So we found some of what you call the variation in the melting temperatures. It is at different temperature it's shown here. For the sample, I think it is sample 3 or no, some samples. Another samples, yeah, it's shown in the top. It is a top sample 101, where the other number it was shown 103. So it is mentioned here. Where 1043 samples we made it in a differential scanning calorimetry test, where it's comparatively we can say the melting point at temperature. What is the latent heat of fusions? It's going to be very, but when we are adding what we call it OBC and certification point also it's going to vary the latent heat, the crystallization it's also varied here. Then this PCM, what we call the flexible PCM can be used for our solar thermoelectric generators, where in which what you call it PCM PV panel or what you call it thermoelectric models. So it may definitely have some little 0.1% improvement. It's an expectations. So how we that work which is still in the underline. I think it is what you call it a thermoelectric generator with PCM, where it's happening when we are adding that Q. It is based upon the sensible heat, then latent heat of evaporation, what you call it, initial next what you call it superheated regions, where what you call it in photovoltaic thermoelectric generation system, PCM used to regulate the temperature of the system, storing the energy to improve its overall performance here. Where it is some photographs which is taken from an building integrated photovoltaic PV panel. They are used with what you call it in microcapsulated PCM, MPCM, and also thermoelectric generator is going to be used, where it is going to be have what you call the better efficiencies. So using this thermoelectric, using what you call the PCM materials, where I like to say some of component of the photovoltaic cell, how that efficiency of photovoltaic cell based upon the operating temperature, it's going to be vary. Where it's probably you've seen that photovoltaic cell efficiency at 298 Kelvin, 1 minus beta, beta is coefficient value, T cell and TA, where the T cell temperature where it is mentioned somewhere in photovoltaic cell efficiency here component, 3 components that was given. When cell temperature is going to increases, its overall photovoltaic cell performance is going to be decreases. Some parameters which is connected to what you call the power factors and that figure of merit value about what you call the thermoelectric generator. When we are adding that one, it's going to improve in a better efficiencies, where in which what kind of that flexible PCM material which is used for what you call it in some heat sink applications, where in a metal foil, where in elastomer it's in the part here, the copper foam. This flexible PCM material which is used in what you call it in different heat recovery applications. I like to give some what you call it in the components here, where what the future research in thermoelectric performance, then the state of art, the cost-effective thermoelectric material, which also relatively offer higher figure of merit values and are stable under critical operating conditions as per their design value or in operating what you call that in manufacturer guidelines. The use of enhanced non-concentrated and concentrated solar thermal device, the integrated with thermoelectric generator system to enhance heat extraction capability and uniform temperature distribution at hot site. The analysis based on design thermoelectric generator coupled heat exchangers, the utilization of both annular and planar type of thermoelectric models across industrial, domestic, and commercial systems. Analysis based on the standalone thermoelectric generator setup for power generation as primary sources, but investigation of nanomaterial-based active cooling methods in domestic and industrial system to improve its heat performance improvements. Where further improvement, where this the retention time can be greatly extended by improving the heat spreading effect of the copper foam and optimizing the structure in the thermoelectric generator. That flexible PCM heatsink the propose a feasible solution to utilize flexible thermoelectric generator in wearable applications. Even in the it can be thermoelectric generator can be so wearable devices it is available like wearable or flexible photovoltaic cell, where then FPCM heatsink can be reused in semi-permanent through the repeating attachment and detachments. It can be this plug and play concept where combat heatsink allows the superior performance compared to the conventional metal heatsink of the same size apart from the high flexibilities. Paraffin wax with OPC exhibit high thermal storage performance and thermotropic flexibility. And PCM absorbs and also high performance PCM used in different applications, where the PCM absorb large amount of heat and the copper foam spread that heat uniformly in the PCM block. The flexible PCM heatsink has compact size with sufficient performance. The conventional metal heatsink has 12 times higher than 9 times heavier than flexible PCM. So it is most important point where we can mention here. It is in conventional metal heat sink. It is a 12 times higher and 9 times heavier than flexible. So if you are using a flexible PCM heatsink, it will be less in weight and less in what you call it and heavier also for the same performance. And to maximize the performance FPSM heatsink, the structural parameters should be optimized. So wherever you go, optimization study always most important. These are couple of references I had it, and like to give my acknowledgement to my the INSA visiting fellow. So it was there supported me to work on something on this thermoelectric geometry model, where this Karnataka State Science and Technology Promotion Society, they given some grant on this solar photovoltaic thermoelectric generator with what you call the latter need storage, some experimental research work, sorry, some research grants in many. And this ICTAC, it is a conference in IIT Madras where the similar work which was presented. So I want to thank them for their permissions. Then Sir Faranara, they're supporting us some couple of events in which we are learned some article where my institute it's given as an opportunity to conduct this kind of program supporting us in this organizing this event. And thank you. If you have any questions, I'm eager to answer. uh, So, any questions if you have, please you can most welcome. Now we have another 1.5 hours time. The session 13 is finished. So if you don't have any questions now. Okay, so you can use what you call it in this remaining one time for your personal work and get ready for what you call it in 6:30 our validatory functions. Formally, we are going to what you call it and organize. It is for your press up time now. No questions. Can we leave now? Yeah.
Yes, sir. No questions.
Comments, no questions. Okay. Okay. Thank you. Thank you, professors. take some break. I think we started from 2 and up to 3. It's almost 3 hours. Now it's 5, so 3 hours. You might be having some personal time. Please, you can have it. Please be joined before 6:30 for the validatory functions. With with your note, so I'm leaving now. So we'll join back again 6:30. Okay, network center, could you stop recording? So
okay,
we
sir.
will start at 6:25.
Yeah, right.
6:15 we can join back.
हेलो
हाँ जी, हाँ जी, हाँ जी. Tell me,
सर,
sir.
अपना टेस्ट 7 PM को होएगा ना टेस्ट?
Pardon? What's your question?
टेस्ट यूनिट टेस्ट अपना
No,
टेस्ट.
once what you call the validatory is over, we will post that test one. So all that the guest they will go off. Then 7 to 8 the meeting link will be on. So you can answer it. That if you have any other question on the multiple choice question, you can interact with us. Me and my coordinator and other supporting staff member will be on online.
ओके सर, ओके.
Thank you, thank you, thank you. So you can stay connected. Don't leave now. So we join on what you call it an online at the time of 6:20. So probably it will be great to us.
Can I stop the recording, sir?
Yes, yes. Stop record now.
Okay,
So
right, sir.
you once the meeting will start, that time please you can record the meeting.